So we're up to 20C, which is about vector multiplication. So far we have added and subtracted vectors and multiplied vectors by a constant or sometimes known as a scalar. Both of these results have ended up with the formation of a new vector. Weirdly enough, when we multiply two or more vectors together, we do not get a new vector. Instead, we just get a number. I know, weird, right? So I want you to have a think. Your challenge is to apply any operations you would like to the components of the following vectors in order for you to get a result of 5. So if we have vector A, which is as a column vector 1, 3, and vector B as a column vector 2, 1, pause the video and see how you could manipulate these. To get an answer of 5, you might use multiplication, subtraction, addition, division, whichever way you can to use all 4 of these components to get an answer of 5. Okay, so hopefully you've had a go. So I know actually when I multiply A and B, the result is 5. So how do I get there? When we have two vectors and we multiply them by each other, what we actually do is we multiply the first component or the I component of each vector, so just the coefficient in front of the I, or our first component in our column vectors. In our case, we'll get 1 times 2. Then what we do, we then add on the multiplication of our second components together. So in this case, we will add on 3 times 1. These are our second components in column form and our coefficients of j in component form. Here we'll get 3 times 1. And notice you can do this either way with columns or component form of vectors. We'll get 2 plus 3 is 5. So this is how we multiply two or more vectors together. And it is called the dot product. Use a dot here to represent multiplication of two vectors. Okay, and to do this or to multiply two vectors, we take the first component A1 times it by the first component of the second vector B1. Then we add on the multiplication of the second two components, so A2 and B2. So just remember that this is always going to spit out a constant. For instance, if we have V equals minus 2i plus 5j and W equals 4i plus 1j, if we were to multiply V and W together, we would write V dot W is equal to minus 2 times 4 plus our coefficients of our j's, positive 5 times positive 1. Then we just simplify this answer, so we'll get minus 8 plus 5, which is just equal to minus 3. So if we have two vectors A equals 2i minus j and B equals 3i minus 2j, we're going to start by finding the dot product of A dot A, or A times itself. I know A is 2i minus 1j. If I'm dotting it with itself, I just write it out like this. So multiply the first coefficients of I and then multiply the j coefficients. So minus 1 times minus 1. Add these two answers together and we'll get 4 plus 1 is equal to 5. And for B, we have B dot B, same process. This time I'm multiplying 3i minus 2j times 3i minus 2j, or times itself. We'll have 3 times 3 plus minus 2 times minus 2. In this case, we'll get 9 plus 4, which is equal to 13. Part C, let's do A dotted with B, 2i minus 1j dotted with 3i minus 2j. Try and put the dot not down the bottom so it doesn't look like a full stop or anything. Put it right in the middle of your line and right in the middle of your two vectors. And I'm just going to show you that you can do this using column vectors in the same way. If you write these vectors in column form, that's fine. You just multiply the first two components, 2 times 3, and you add on minus 1 times minus 2. We'll have 6 plus 2, which is just 8. The last one is a little bit more difficult, but we follow the same routine. Just like any algebra, remember to do what is inside the brackets first. So the first thing we have to do is figure out what a plus 2b actually is. I'm going to start by multiplying b by 2. So I'll have 2 times 3 is 6. 2 times minus 2 is minus 4. So I'll have 6i minus 4j. Then remember we've got a plus my 2b. So I'll have 2i plus 6i is 8i, and minus 1j minus 4j is minus 5j. So we've figured out what a plus 2b is. Now I've just got to multiply that vector by itself. This is nice. We'll get 8 times 8 is 64, and minus 5 times minus 5 is 25, plus those answers together. Just a reminder that a times b or a times any vector, right? It doesn't always have to be a positive answer. That was just coincidence that all of those were. It can even be 0. Now we're going to look at something a little bit differently because I want to investigate these relationships between the dot product and the length of vectors a little bit. So we're going to compute the length of a squared for question E. Remember that the length of a, we're going to take the square root of my first component squared plus the second component squared, 2 squared plus minus 1 squared. And in this way, we'll get the length of a is root 5, but remember we're trying to find the length of a squared. If I square the square root of 5, I'm just going to get 5. And if you recall, this was the same thing as a dot a. So first, let's calculate what a plus b is. I know a is 2i minus 1j plus b, which is 3i minus 2j. Add the like terms in quotation marks, and we'll get 2 plus 3 is 5i, minus 1 minus 2 is minus 3j. I'm also just going to calculate a minus b. We'll get 2i minus 3i, and then minus 1j plus 2j because of the minus and the minus. And in the end, we get minus 1i plus 1j. Okay, now we can take the length of both of these vectors and square that length. So the length of a plus b, well, that would be the square root of 5 squared plus minus 3 squared, which equals the square root of 34. Okay, remember I want to square this length, so I'll just get just 34. The same with a minus b, we can find the length of this in the same way and then square it to get the length of a minus b all squared. The length of a minus b is root 2. If I square this, I'll just get 2. Now I can complete the question. The length of a plus b squared is 34, and I'm going to subtract the length of a minus b squared from this. 34 minus 2 is just 32. So here are some properties of dot products. So for instance, when you multiply two vectors together, say vector a and b, okay? It doesn't matter what order you multiply them. A times B would give you the same answer as B times A. If you times a vector by the vector 0, okay, you will just end up with 0. If you have vector A times vector B plus vector C, you can distribute this like normal. So you could get A dot B plus A dot C, similar with usual multiplication. Now, like we hinted at before, when you have a vector dotted with itself, this is actually going to equal the length of that vector, all squared. Lastly, if you have a constant, say constant D, times the dot product of A and B, you could take the D inside and figure out what D times A is first and dot this with B. We're just going to prove theorem 4. Feel free to prove the other ones or have a go at proving them. I'm going to break this down into the left-hand side and then the right-hand side. If we look at the left-hand side first, we know that A dotted with A would be equal to A1 all squared plus A2 all squared. In your proof, make sure you have enough steps in here so it's clear to the examiner how you get from the start of the proof to the finish. Now we know what the dot product of A and itself is, let's figure out what the length of A squared is, and hopefully these will equal each other. So we look at the right-hand side separately. I know the length of A, well, that's the square root of A1 squared plus A2 all squared. Okay, if I square this, I'll just remove the square root sign, and I do actually end up with A1 squared plus A2 squared, which is the same thing as my left-hand side. So in conclusion, we can conclude that the right-hand side and the left-hand side of this equation that we're trying to prove is the same. Therefore, A dot A is equal to the length of A squared, and both of these are equal to A1 squared plus A2 squared. Now, in the next video, I'm going to go through why the dot product is important, and this is a really essential, I guess, part of the topic to understand.